Hey, welcome. In this video I'll go through current-driven instabilities, and these are instabilities which are caused by the current which is put through a plasma to try and compress it or provide some external force on the plasma. So this is the same process as a can crusher you may have seen, which has a metal can. You pass a very large current through it and this compresses the metal. The same thing happens with the plasma. But this large current can cause instability, so the whole thing can twist into a kink, for example. And this is seen in some of the earliest experiments, and is still seen today in current day tokamaks, but in a different form. So I'll start by looking at toroidal pinches. These were an early example of a machine designed to compress plasma by passing a current through it. So a Z pinch, seen already, was a cylinder. Pass a current through it and this compresses the plasma. A toroidal pinch is the same thing but in a torus. So you pass very large currents in a toroidal machine, compresses the plasma, and as we'll see, produces instabilities. So my favourite one of these was the Perhaps-a-tron, which was created by James Tuck at Los Alamos in the early 1950s, and it has a kind of coil like this down the middle. So this is basically a transformer coil. So you have a current in the coil, and then you change the current in time. So you produce an electric field which goes around the machine here. So you have an electric field which drives a current, and that current compresses a toroidal plasma. So in here there's a toroidal plasma which is created and heated by the current and then compressed. So you have a plasma kind of cross-section like this, like a torus like this. And the current driven in the plasma creates an inwards force, and the idea is that this then compresses the plasma. So this is called the Perhaps-a-tron, because perhaps it would make fusion. Now what was seen in these early experiments was that if you looked from the top of the machine, so if you looked from this top part down, there's some early experiments by Carruthers and Davenport, for example, where if you can do this experiment with a glass tube, and so you see the plasma as a donut from the top. So the winding is this coil is this winding down the center, and it's driving an electric field around the outside here. This is the electric field. Now the electric fields go around here. What was seen is that these plasmas would start out as like a donut like this, but then they would rapidly deform and twist, and you'd end up with plasmas which were kind of twisted like this. And they would kind of deform and break up into pieces. So you're driving a current through the middle. But the whole plasma would twist into a helix, and then break up. So very quickly break up into pieces like this. As there's a Carruthers paper in 1957, and this was not particularly surprising. So people knew that this should happen. It was predicted theoretically before this was seen by Krushkalanj and Schwarzschild in the 1950s. But people hoped that by compressing quickly enough that you could achieve high temperatures and pressures before these instabilities became too big. And then when it was found that this was not possible, people tried various ways of stabilizing it. And two main ways are firstly to put a wall next to the plasma. So this is like stabilization methods. And the idea here is that you have a metal outside the plasma, but it's quite close to the plasma, so there's like a metal wall here. And then we have the plasma inside, and the plasma is kinking and trying to move like this. So the plasma is moving. This is the wall here. So what's happening here is that the magnetic fields, which are drawn here, there's a magnetic field between here. There's a B field in there. And because the wall is conducting, as the magnetic field at the wall changes, there's a current driven at the surface of the wall, and that current essentially opposes the motion of the magnetic field through the wall. And so if the wall is a good conductor, the magnetic field is trapped between these two, and so as the plasma moves towards the wall, the magnetic field increases. So these kind of field lines here are kind of stuck in here. So the field is now higher in here than it is over here, because the field lines are now closer together, and so this increases the magnetic pressure and pushes back on the plasma. And so a conducting wall sort of resists the motion of the plasma. And if you had a perfect conductor right next to the plasma, then this would prevent the plasma from moving. So this is what we discussed earlier with things like internal modes. This, however, is not usually possible, so you have some finite resistivity, usually because you also need coils on the outside of the plasma to control it. And so if you made a perfect conductor, those coils couldn't have any effect on the plasma. And so you have a finite resistivity, and so this eventually will leak through the wall and lead to instability. So this is one way of stabilizing it. The other way is to impose a magnetic field. And in a tokamak, this is the toroidal field. So in this straight line here, I'll just draw the vessel again. If you have a plasma which is kinking like this, so what we do is we put a strong magnetic field through the middle of the plasma. So we put a strong external magnetic field, and what this is doing is the field line bending of this external magnetic field. So if the plasma is moving this way, this requires bending the external magnetic field, and that takes energy. So if you remember, there are terms in the delta W equation involving compressing the magnetic field, which is stabilizing here, or bending the magnetic field, which is this term here. And so by putting a strong magnetic field on the outside, using external coils, you can suppress this instability. The problem is, if you, with these early machines, the heating of the plasma was due to the compression of the plasma. So this compression was essential for the machine to work. And if you put a very strong magnetic field through the plasma, you also prevent the compression, because you're now compressing the magnetic field and you're compressing the plasma. And so there were a whole series of machines called stabilized pinches, such as the Zeta, so the zero energy toroidal assembly. So that was the Zeta experiment. It was a UK experiment, but it was not a tokamak, so that it did have a wall and it had a toroidal field, but it was a very weak toroidal field, so much weaker than a tokamak would be today. And so the idea of this was to suppress the kink for long enough that the plasma could be compressed. But the strong magnetic field wasn't used because that would prevent the compression or reduce the compression. And unfortunately, it was found that this was not sufficient. There were still instabilities in Zeta, which prevented the full performance. But some interesting effects were seen, that occasionally the plasma would reorganize itself into a state with the lower fluctuations. And this led on to research on reverse field pinches. Now, tokamaks use quite different methods for heating the plasma. So they don't rely on compressing the plasma using external currents. Instead, the currents and the external fields are there for stability, and the external heating comes mainly from things like neutral beam injection or from radio wave heating. So that there is a heating due to the ohmic heating of the plasma, but it's usually quite small in high performance machines. And so it's no longer a concern that if we impose a very high magnetic field, that we can't compress the plasma, because that's not the main method that we're heating it by. But these current instabilities are still seen in tokamaks, and there are three main instabilities I'll talk about in later lectures. The first is very like the instability seen in pinches, and this is something called the sawtooth. Because what's seen is, if you have the tokamak, I'll just draw a colloidal cross section like this. So we have various lines of sight of things like soft X-ray cameras. So these might go through like this, for example. And if you have the hot core of the plasma is like this. If you look at one of these lines of sight through the middle, it's like a core line of sight, what you'll see is, under the right conditions anyway, the wrong conditions. So the time, then this is the soft X-ray. So which is essentially it's a measure of the temperature of the plasma, because as the plasma gets hot it emits X-rays, and so this is a simple way of measuring the plasma temperature. And what you see is on these lines the temperature is increasing and the X-ray emission is increasing, and then suddenly it will drop, and you get a repeating instability like this. So on the soft X-ray signal it appears like a quasi-periodic, so it has a period, but it varies a little bit, but it's building up and then crashing, building up and crashing. And if you look at a different line of sight, so let's say choose one of these outside here. So this is outside the edge. What we'll see instead is that the signal kind of drops gradually and then has pulses going up. So at roughly the same time that the core drops, you see pulses arriving just outside the edge. And what's happening here is that the heat and some particles from the core are occasionally being thrown out by an instability. So there's a current building up in the core. What happens is the current becomes there's too much current in the core, and so the safety factor drops. You see a crash, heat is thrown out, and you see a pulse of heat arriving outside, and then the whole process continues or repeats. So you have a current building, diffusing into the core, building up, and then a crash, and then it keeps going. So the other kinds of instabilities that are commonly observed are things like external kinks, and the related instability, which is called a resistive wall mode. So these often set the maximum performance of a machine because they're driven by a combination of the current and the pressure. So if you want to get to highest pressure, highest current, then this ultimately limits the performance. And it can be quite a dangerous instability because it involves the entire plasma moving. And so it can essentially throw the plasma against the wall of the machine. And so we'll cover these later. So these are dangerous because they can lead to instabilities, can lead to disruptions of the plasma. And lastly, the final one we'll look at is called the tearing mode. Or the related neoclassical tearing mode, or NTM, which is a tearing mode driven by neoclassical effects, so driven by the bootstrap current. And what's seen experimentally is that the temperature of the plasma, so from the core to the edge, so this is like radius, so we're looking along through the plasma here, so we're looking along a line of sight like this. So you might have a laser, so Thompson scattering measurement, you measure the temperature along a line. What's you hope seen is that there's some kind of temperature maximum, and the temperature, this is in the hot core. But what's seen with a tearing mode is that the temperature instead has a flattened region. And so there's a region of the plasma where the temperature is essentially flat, and this region here, this is the width of a tearing mode. So in this region here, the plasma is not confining the heat. So heat is just leaving straight across this region to the edge. And so the temperature in the core now drops, and so these degrade the performance of the plasma, and they can grow. So this region can get bigger and bigger, and things like trigger other kinks and other instabilities. So these essentially just degrade the performance. And because they're driven by neoclassical effects and tearing modes, so they are partly driven by current, by pressure, and so these also come in and become important at high pressure, so high performance discharges.